Hello folks, today we are going to do the second half of our gas laws lecture. As you recall, last time we were talking about gases and what makes them special. So the idea here is that gases have different chemical properties but have very similar physical properties. Volume, pressure, and temperature can be easily predicted regardless of its identity. Whereas liquids and solids do not follow these rules. So we were able to look at mathematical relationships and gas laws as a theory to explain how gases behave. So last week we looked at several laws, and I just wanted to recap them for you. So first we had Boyle's law, which looked at the relationship between pressure and volume, and found that they had an inverse relationship, where if pressure was high, volume was low. The next law we looked at was Charles' law, which looked at the relationship between pressure and temperature, and found that as temperature went up, pressure also went up in a direct relationship. Third, we looked at Gay-Lussac's law, which also saw that as temperature went up, volume went up. And when we look at all three of these laws together, we could see a relationship that pressure and volume were in the numerator and temperature was in the denominator. And so we could combine them into one main law called the combined gas law. So let's practice with one of those problems just to see where we're at. Here are our formulas. And the main one we're looking at right now is here. And our question says, a weather balloon filled with 2.94 liters of helium at a location where the pressure is 1.06 atmospheres and the temperature is 32 degrees Celsius. What will be the volume of the balloon at an altitude where the pressure is 0.092 atmospheres and the temperature is negative 35 degrees Celsius? So again, with these numbers, it's always best practice just to write down your variables and just kind of place where all those numbers belong. The other thing you should have seen is hopefully that we have our Celsius numbers written here. And if you remember from last week, we can't use Celsius, we have to use Kelvin. So for both those numbers, we're going to add 273. So I like to list out all my variables. So the original half of the equation, P1 is 1.06, V1 is 2.94, T1 is 32 plus 273. My second side of the equation is 0.92. We are solving for the second volume and then our temperature in Kelvin. So we plug all of that into our equation, and there you can see those Kelvin numbers on bottom. We're going to cross multiply. And when we write it all out, that should follow. We can simplify and then solve for x. X equals 3.12 liters in this case. All right, so we're going to move on to one other big formula, and there's some pieces that we have to put in there. So first I just want to introduce something called Avogadro's law. We're not going to do any calculations with it, but it's going to give us one other piece of our ideal gas law when we get there. So Avogadro, remember, are 6.02 times 10 to the 23rd molecules. Avogadro didn't actually calculate Avogadro's number. We just named it after him because of the work that he did led to the calculation of that value. What Avogadro did determine was that equal volumes of gases at the same temperature and pressure have equal number of particles, regardless of the type of gas. So if I have water vapor and I have oxygen, and I have them in separate containers that are in the same conditions, the same volume, same pressure, same temperature, we would see that it's the same number of moles. So we can therefore see a relationship between volume and the number of moles. So V1 over N1 equals V2 over N2. And this fits into what we've seen before. Again, V1 was always in the numerator with our combined gas law. It's still in the numerator here. So when we add in Avogadro's idea that moles and volume have a relationship, we get one more formula here. So with Avogadro's number, we could make one giant combined gas law that now includes moles. So this is big and kind of ugly. We're, again, not going to use this whole thing. Just leads us to something called the ideal gas law. So like we saw with our other gas laws, we're looking at ratios. And the way the ratios are set up is they're always going to be the same number. So we can basically solve one side of this equation and call it R, that it's a constant. And that's what we call the universal gas constant. You will not have to memorize R. We will always give it to you, but it is looking at that relationship between volume and moles, and that ratio would always be equal. So our equation is showing us a before and after scenario where one variable changes and we can predict how the others will change in response. So instead of doing that for both sets of data, we're just going to do it for one side of the equation. So we get information as a snapshot of the gas without changing anything. And we can move some things around and give us that ideal gas law. So one version of this, right, we're just solving for one half of the equation, looking at one data set. And we said that we know that the ratio on both sides is equal, and so we're just going to call that R. So if we move a couple variables around, we get our ideal gas law of PV equals nRT. And that's the equation that we use when we are doing our ideal gas law. So PV equals nRT. Now, if where all these numbers came from and how it was derived is confusing you, that's okay. For our purposes, we're going to talk a little bit more about what makes something an ideal gas and then using this formula. So our ideal gas law, PV equals nRT, just to rehash what those variables mean. So P is our pressure. Now, last time we talked about the different units for pressure, atmospheres, millimeters of mercury, kilopascals. You might need to convert. We won't be doing that today, but just know, should you come across problems, they might not always be in the same units. Volume needs to be in liters. And again, you may have to convert. N is the number of moles. It has to be moles, not grams. And then R is our universal gas constant. And those are numbers that are always provided to you. Now, the constants don't change, but they're different values depending on your pressure unit, because that's what can change. Volume is in liters. Volume is always in liters. Pressure can be converted. Temperature is always going to be in Kelvin. And our amount will always be in moles. So the gas constant has a really big, ugly unit where everything would cancel out once it's plugged in. And again, the conversion you're most likely going to see from us is that Celsius to Kelvin conversion. So how do we use our ideal gas law? Here is one example. At standard temperature and pressure, what is the volume of 1 mole of oxygen gas? Now, looking here, you might be thinking, Ms. Rusnak, you only give us one number. What does that mean? I didn't give you just one number. I gave you two other numbers as well. If I say it's standard temperature and pressure, well, standard temperature is 0 degrees Celsius. which will turn into Kelvin. And then our pressure will also be one of those standard values. So which one do we want to use? It really doesn't matter which one we pick because I didn't define anything, but here we go. If I give you an R, I'm asking specifically for atmospheres. So on our pressure scale, 0 degrees Celsius is 273 Kelvin, sorry, that temperature scale, and the pressure scale is atmospheres. So 1 atmosphere is our standard pressure. So now I can just plug in everything. R is given to you, it is a constant, and that number is always available to you. Pressure is 1 atmosphere, volume is what we're solving for, N equals 1 mole, and temperature is 273 K. We plug that all into PV equals nRT, and we get 1x from our atmosphere. X is our unknown, 0.0821 times 273, and I missed a 1, for our 1 mole. So PV equals nRT. And now I can just solve for x. So 0.0821 times 273 is a number 22.4. So does that number look familiar? Hopefully you are thinking of our mole map, and when we did something with volume of a gas, we looked at a number of 22.4 liters per mole, and we had specified that it's standard temperature and pressure. So Avogadro's number and the ideal gas law is where 22.4 came from, in case you're curious. So let's do another practice problem. Calculate the pressure of kPa and of 0.412 moles of helium at 16 degrees Celsius and occupying 3.25 liters. So again, write out your variables, make sure you're plugging them into the proper spots, and then you have to solve. So go ahead, give that one a try if you want to pause the video. So I asked for kPa, so R is 8.314. Okay, and now we can again write down all of our variables. You were given Celsius, so I hope you converted to Kelvin. Plug everything in. Simplify and solve for x. X equals 304.6 kilopascals. So with our ideal gas law, no gas is really ideal. This is really just a concept based on some theories and presumptions. The actual ideal gas law formula that accounts for some things is very complex. This is a simplified version that allows us to do our calculations. Hydrogen and helium are the closest to being an ideal gas. And the main reason that no gas is ideal is that the kinetic molecular theory requires that gases do not attract or repel each other, but they actually do. So attraction and repulsion has to deal with our intermolecular forces from a couple units back. They do exist, but we have to ignore them for our kinetic molecular theory. So for our ideal gas law to work, there are assumptions we have to make. So those assumptions we call the kinetic molecular theory. And it starts with the idea that gases are mostly empty space, tiny spread out particles. And because they're so far apart and gas molecules are so tiny, we're basically just counting the space around them and ignoring the particles. The second assumption is that an elastic collision occurs between gas particles with no loss of energy. So if two gases do collide in that big vastness of space, that they don't lose any energy, they just continue to bounce and go along the way. The third assumption is that gas particles are constantly in motion, which does make sense, right? Our velocity of our gas is related to that kinetic energy. And as long as there is some kinetic energy in heating the gas, there will be some motion of those gas particles. That fourth assumption we already mentioned, but there are no forces of attraction or repulsion between gas particles. We are ignoring intermolecular forces and saying they do not exist in this case. And that the kinetic energy of a gas depends on the temperature. So the idea that as temperature increases, the energy and speed increases, which we saw back in our thermodynamics unit. So again, an ideal gas doesn't truly exist, but it gives us a jumping off point. So real gas molecules do have volume and they do attract one another. They have IMFs. And while a gas can never truly be ideal, some gases are more ideal than others if they meet the following conditions. So we want to be at low pressure where there is more empty space between molecules. We want to be at high temperature where there's more energy that allows us to overcome intermolecular forces. We want to have weak forms of intermolecular forces. So something like helium is nonpolar and it's covalent. So that would have a really weak IMF, whereas water vapor can still hydrogen bond. And so if those vapor molecules come near each other, IMFs are going to come into play. And then we want to have a low molecular mass with few electrons. And again, those electrons are going to play into those intermolecular forces. So that's why hydrogen and helium are the closest to ideal. Very low molar mass, very weak intermolecular forces. And when we're at low pressure, high temperature, that is when the conditions are most ideal. So let's do a couple other practice problems just to finish up. So what is the volume of 5 moles of water vapor when it's at STP? So I could go through and do PV equals nRT. I could throw in my constant and I could plug these things in. But there's a simpler way. What value do we have when we're at STP? 22.4 moles, liters per mole. So with 5 moles, we can set up a fence. 1 mole is 22.4 liters. So 5 times 22.4 is 112 liters. So we could go through and we could plug that into our ideal gas law, PV equals nRT. So my pressure could be 1 atmosphere. My volume is still my unknown. And then N is 5. R would be, R is our gas constant that if I'm using ATM as my pressure, it'd be 0.082. And then standard temperature is 273. So I could multiply all of that out. And again, my question here that I'm solving for my volume, I get 111.93, which would round to 112. So because our ideal gas law is what gave us 22.4, and because we're at standard temperature and pressure in this case, we can just use that good old 22.4 that we used in stoichiometry, or you could plug it in to our PV equals nRT equation. Go ahead and give this example a try. Okay. And in this case, R, because we're given kilopascals, would be 8.314. So go ahead and plug these in and see if you can solve for V. Okay, so again, I highly recommend writing down your variables. Your pressure, your volume is what you're solving for. N is 4 moles, T is 300 K. In this case, no conversions are necessary. You just want to be making sure you're using the correct R value. And this 8.34 is the value that you use for kilopascals. And when you plug everything in, hopefully you get that the volume is 24.9 liters. 400x equals 4 times 8.314 times 300. Solve for x. All right, folks, thanks for tuning in today. You have a great day.